Okay, our last section for this chapter is factoring special polynomials, and some of these we've already kind of talked about as we've done other things that come up in the chapter, and we've already talked about them, but we're going to kind of deal with them all together here again now. So the three types that we're going to be looking at are perfect square trinomials, difference of squares, and trinomials with two variables. So when we did that worksheet that day, we did some difference of squares and the trinomials in two variables. We kind of talked about those earlier on. We had them as star problems, but we did them in class. So we're going to actually cover them in a little bit more detail here now, or ones that are a little harder. Okay, so the first ones we're going to do are perfect square trinomials. And basically a perfect square trinomial is similar to like a perfect square number. A perfect square number is something that can be written as a factor times itself. So a perfect square trinomial basically has two factors which are exactly the same. So a factor times itself. And we've already basically learned how to factor perfect square trinomials, because you still can factor them using the methods of trinomial factoring methods that we learned earlier. For example, if you had type x squared plus bx plus c, you still look for two numbers that multiply to give you c and add to give you b. You can still do it that way, and you just should notice when you're done that if it is a perfect square trinomial, the two factors would be the same. For example, x squared plus 8x plus 16, two numbers that multiply to give you 16 and add to give you 8 would be 4 and 4. And when you write the factors down, you get x plus 4 times x plus 4, which is a perfect square trinomial, because that can be written as x plus 4 all squared. So, and if the type is of ax squared plus bx plus c, you can also use other methods to factor a perfect square trinomial, but sometimes the numbers can be, especially if it's ax squared plus bx plus c type, numbers can be sometimes large, and if you recognize as a perfect square trinomial, it's really quick and easy to factor rather than having to do the decomposition method or whatever. So let's take a look at some different types of examples now. So the first ones we're going to do are the easier trinomials, and they would be three examples here we have. So the first one is x squared plus 10x plus 25. So if you think about the old way we factored, we would be looking for two numbers which multiply to give you 25 and add to give you 10. And that would be 5 and 5. So when the two numbers are exactly the same, you'll end up with factors. Of course, when you have an easy trinomial, you can go straight to your factors, because the first two terms have to be x and x, and you'd have to have plus 5 and plus 5. So therefore you have a perfect square trinomial, x plus 5 times x plus 5. Two factors are identical. And the second one here, if you again use your old methods, you're looking for two numbers which multiply to give you that last term 64, and have to add to give you that middle term of negative 16, which would be negative 8 and negative 8. And when we factor, again, it's an easy trinomial, so you can go straight to the factors. You don't have to use decomposition. So you can go x minus 8, x minus 8. And there you have a perfect square trinomial, because the two factors are identical. Again, you could write this, the first one as x plus 5 all squared. That would also be fine to write it like that. Or you can write this one as x minus 8 all squared. And the last one, you'd be looking for two numbers which multiply to give you 100 and add to give you 20. And that would be 10 and 10. So again, the same two numbers, and the factors would be x plus 10 and x plus 10, or x plus 10 all squared. So if we look at those factors and those trinomials that they came from, we can see if there's a relationship between, how do you know, like when it's a perfect square trinomial, how can you look at the trinomial to start with and see that it's a perfect square trinomial? And you should notice that the square root, there's two ways you can look at it. The square root of the last number doubled gives you the middle coefficient, right? So square root of 25 is 5, doubled is 10. Look at this one, square root of 64 is 8, doubled is 16, but there's a minus there, but that's okay, because the last term is positive and the middle term is negative, so that means you have two negatives to multiply to give you a positive and add to give you a negative. And this one here, if you look at the last term, square root of that is 10, and doubled would give you 20. So that seems to be a pattern. And some people look at it from the middle coefficient and say if I take half the middle coefficient, which is in this case the first one, half of 10 would be 5, and then you square it, you get 25. So you can look at it from that direction as well. So that's basically what this is saying here, that a perfect square trinomial basically has this type of a form. It has a squared term as the first term, a squared term as the last term, and in the middle it's a combination of those two, the square roots of both of those terms, but doubled. You could also have it with squared term first, squared term last, and then double the product of those square roots of those two things, but subtract it, because that would be, again, a perfect square trinomial with two factors that have a minus in them. You will never ever get a perfect square trinomial if this last term here is a negative, because that would mean there'd have to be two numbers which multiply, two numbers that are the same that multiply to give you a negative, and that's impossible. So when we're looking at relationships, we can look to see if we can find a number, if half of this number right here, half of b squared, should give you c. Okay, so c should be, take half of b and square it and you should get c. Or again, you can work backwards and say if you square root c and double it, you should get b. Okay, so let's expand these and see if those patterns actually do, because these are perfect square trinomials. The factors are in perfect square format, and if you expand them, you will see that that pattern does hold true. So we've got x plus 2 by x plus 2, and if we expand those, we get x squared plus 2x plus 2x plus 4. And that's going to give you x squared plus 4x plus 4. Or we could use the pattern up above, knowing that this is a perfect square trinomial. We can use the pattern and say, well, that should have first term x squared, last term 4, and then twice the product of the square root of those two things, or twice the product of these two numbers here. So twice that would be 2 times 2x, which is the 4x term. So let's try that pattern for this one. So we know that the first term, when we multiply, we could multiply it out, like I said, like we did here, just by expanding it. But let's just expand it using the shortcut rule, the little pattern. So we have x squared, and then we have the product of these two things, but doubled, so that would be minus 2 times 3x. And then plus the square of the last term, which is 9. So that would be x squared minus 6x plus 9. And if we use that pattern again here, and again, you don't have to use the patterns if you don't want. You can multiply it out as x plus 6 times x plus 6. But let's use the patterns again. We'd have the square of the first, then we would have plus twice the product of 6 and x, and then square of the last. So that should give you x squared plus 12x plus 36. Alright, so now let's start off with the trinomials and see if we can come up with the factors. So we know that this is a perfect square trinomial because the first term is a perfect square, the last term is a perfect square, and the middle term is twice the product of those two square roots. So we would know that the factor should be the square root of that, the first term, the square root of the last term, and it should be plus plus, or x plus 1 all squared. And this one here again, this is a perfect square, this is a perfect square, this is x times x, this is 4 times 4. So when we take the 4, and we know, again, I know we know these are perfect square trinomials, but I'm just showing you the pattern. That's 16, the square root of that is 4, the square root of x squared is x, and double it is 8x. So it has that pattern. So we know the factors then should be the square root of x squared, which is x goes in the first spot, and the square root of 16, which is 4, goes in the second spot, and they should both be positive again. or x plus 4 all squared. And again, you can double check using your FOIL method. X times x will give you x squared, plus 4x will give you the 8x, and then 4 times 4 will give you the 16. Alright, so this one here, again, is a perfect square trinomial, and the first two terms would have to be x and x. The last two terms would have to be 7 and 7. This time they'd have to have minus because you want to get minus 14x. Minus 7x and minus 7x is going to give you the minus 14x when you multiply those out. So that would give you x minus 7 all squared. And the next one is again a perfect square trinomial. You got x and x, 9 and 9, and 9x doubled does give you 18. So that would be, factors would be x and x, 9 and 9, but plus and plus. Right? There's the 9x and the 9x when you do the FOIL give you the 18, right? Sorry, because it's in the way there. So this would be x plus 9 all squared. And the next one, this is a perfect square, x times x. This is a perfect square. The square root of the top and the square root of the bottom would be 5 over 2. So that would give you, it's supposed to be an arrow there, it doesn't look like one, does it? Alright, so this would be x and x, 5 over 2, and 5 over 2. And you need a minus between them. Or x minus 5 over 2 all squared. And the last one would be the square root of 1.44, which would be 1.2 squared gives you that, and x times x gives you that. So you would have x and x, 1.2, 1.2, and inside would be positive and a positive. And again, just double checking to make sure it is a perfect square trinomial. 1.2 times x doubled does give you 2.4. So it does have that pattern of a perfect square trinomial. Oops. Alright, so the next example asks you to see if you can figure out what to do in the box to make it a perfect square trinomial. So we know that if this is 12, then half of that squared should go in here. So half of 12 is 6, and 6 squared is 36. So we know that 36 is what we need in there. In order for this to be a perfect square trinomial, we take half of the middle term, which is negative 10, over 2, which is negative 5, and that squared would be 25. Oh, and I forgot to factor the first one. The first one would be x plus 6 all squared, and this one would be x minus 5 all squared. And the next one, you need half of 3, which you can keep as a fraction, 3 over 2, or you can write it as a decimal, 1.5. But then when you square that, it's going to be 3 over 2 times 3 over 2, which is 9 over 4. So that's going to be x plus 3 over 2 all squared. Square root of this, square root of 9 over 4 is 3 over 2. And this one, if it's a perfect square trinomial, you want half of negative 1.2 divided by 2 is going to be negative 0.6. And if you square that, negative 0.6 times negative 0.6, you're going to get 0.36, I believe. Right, because 0.6 just times 0.6 would be, if you ignore the decimal, it's going to be 36, but then there's 2 decimal places, so that would be 0.36. And then your factors would be square root of this would be x, square root of this would be 0.6, and you would want minus in between. And that would be x minus 0.6 squared. So let's look at the pattern now for when you have a trinomial with something in front of the x squared that can't be factored out as a GCF first. So when you have those ones, how do you identify which ones are perfect square trinomials? So let's start out by just multiplying some perfect square trinomials, multiplying some factors of perfect square trinomials that end up having that form of ax squared plus bx plus c. So the first one there, if we use our shortcut rule again, we know that it's going to be the square of the first. Now, I mean, if you want, you can just do 3x plus 2 times 3x plus 2. I'll do the first one the old way, and do the last two the shortcut way. Okay, so 3x times 3x is 9x squared, and you got your plus 6x plus 6x. So you can see that it's going to be the product of 3x and 2 doubled, right? Because they together will form 12x, and then plus the 4. So you end up with 9x squared plus 12x plus 4. This one here, if we expand it using the shortcut, we know that it's going to be the square of the first term, which is going to be 4x squared, and there's going to be negative twice the product of 2x and 3, so that's going to be negative 12x, because 6x doubled is going to be 12x, and then we've got negative 3 is going to be positive 9. And this one here, if we do the shortcut again, we got the square of the first term, which is 5x times 5x, or 25x squared. And we've got twice the product of 5x and 6x, which is going to be 5x and 6, which is 30x, so doubled is going to be 60x. And then square of the last is 36. And again, for B and C, if you did it the same way we did A, you should get the same answer. So if you look back at patterns, you can see that the same kind of thing that happened in the first one is happening, that the first term here is the square root of that. The second term in your binomial factor is the square root of that. And then inside here, we have the twice the product of the first and last term square root. So it's basically the same kind of pattern as what we had in x squared plus bx plus c. I just want to highlight that there, that the middle term, the coefficient of the middle term is always double the product of your first and last terms there, right? Alright, so let's take a look at some of these examples here now. And it tells you that they're perfect square trinomial, but I'm just going to confirm for you that they are perfect square trinomials. So we look at this one is a perfect square, 2x times 2x will give you that. This one is a perfect square, 3 times 3 will give you 9. And then take the square root of the first term, which is 2x, the square root of the last term, which is 3. 2x times 3 is 6x, and doubled will give you 12. So it is a perfect square trinomial. So based on the method we just talked about, we should have as our factors, we should have the square root of 4x squared, which is 2x, and we should have the square root of 9, which is 3, and there will be a plus in between. And that would be the factor 2x plus 3 times 2x plus 3, all squared. Right? 2x plus 3 all squared, that's what it means. So this one here, we would be looking for the square root of that would be 5x, and the square root of this would be 2. So our perfect square trinomial factors would be 5x plus 2 by 5x plus 2, or 5x plus 2 all squared. And again, if you check the pattern, 5x squared is 25x squared. 5x squared is 25x squared, and twice the product of 5x and 2 is going to be 20x, and then square of the last term. And this one here, the square root would be 3x. This one here would have a square root of 7. And if you multiply 3x by 7 and double it, you will get 42. But because the middle term is negative here, we have to have a negative in between these two. So the factors of this trinomial will be 3x minus 7 times 3x minus 7, or 3x minus 7 all squared. And this one here, square root is 6x, and the square root of 25 is 5, and if you multiply those two terms by each other, you get 30x doubled does give you 60. So the factors are 6x plus 5, 6x plus 5, or 6x plus 5 all squared. This one has a perfect is a perfect square because 1 times 1 is 1. And this is a perfect square because 3x times 3x is 9x squared. But this time we need to have 1 minus 3x inside because the middle term is negative. And 3x times 1 doubled is 6x. And this one here is a combination type, but you can still do it the same way. This has square root of 9x, this has a square root of 4y. And if you multiply those two things by each other, you get 36xy. Doubled does give you 72xy. But the middle term is negative here, so we've got to remember that in our factors, we have to have 9x minus 4y times 9x minus 4y, or 9x minus 4y all squared. Okay, so now we're going to try some questions where you have to figure out what needs to go inside the box to make it a perfect square trinomial. So we have to look at the first term is a 5x squared, and the last term is a 2 squared. So if we double that product of 5x and 2, we get 20. 5x times 2 is 10x, and so we need a 20. We need it doubled in there. And that would have factors 5x plus 2 all squared. This one here, the square root of the first one would have to be 7x, and the square root of that would have to be 1. So if we take the product of 7x and 1, we get 7x. Doubled would be 14. And our factors then would be 7x, though, minus 1, because our middle term is negative. 7x minus 1 squared. Next one, this square root would be 6x, and this square root would be 9. And if we want to figure out what goes in the middle, we need to take the product of 6x and 9, which is 54x. Doubled is going to be 108x. So we need 108 in the box. And our factors would be 6x and 9, but with a minus sign between them. And we'd need 6x minus 9 times 6x minus 9 all squared. Or 6x minus 9 times 6x minus 9 is 6x minus 9 all squared, sorry. Now just looking at this one here, 6x minus 9 all squared, that would not be completely factored, because if I were given that originally, I would take the GCF out of the first 3 terms before I start, because I can see that each of the factors of 6x minus 9 has a GCF of 3 that could come out. Anyway, but you're only asked to write it as a perfect square trinomial, so that is correct. All right, so this one here, the square root of 21 is 11x, and the square root of 64 is 8. And if you take the product of 11 and 8, x is going to be 88x, doubled is going to be 176. So we need a 176 in here. But there's a minus sign between them, so that means between our terms of 11x and 8, we want a minus 8. So 11x minus 8 times 11x minus 8 would be the factors, or 11x minus 8 all squared. Square root of 1 is 1. Square root of 10x squared is 10x. 100x squared is 10x, sorry. And twice the product of 1 and 10x is 20x. And then our factors would be 1 plus 10x. And the last one, square root of the first term is 3x. Square root of the last term is 5y. And if you look at the product of 3x and 5y, that's 15xy. Doubled is going to be 30xy. So we would want 3x and 5y, but we want a plus sign between them. So the two factors would be 3x plus 5y times 3x plus 5y, or 3x plus 5y all squared. All right, so the next type of factoring that we do is difference of squares. And we did do a worksheet, if you remember, earlier in the chapter, and there was a couple of difference of squares in it. We talked about it quickly, but basically, when you multiply two binomial factors that are almost the same, except the only difference between them is one has a positive between the terms, and the other one has a negative between the terms. When you multiply those out, you'll always get the inside and outside of your FOIL process, or basically this distribution and this distribution. Those products will always cancel each other out. And so that basically results in something that looks like a squared minus another square term, or a perfect square minus a perfect square, which is what we call a difference of squares. Difference because of subtraction between them, and the first and the last term are both perfect squares, so it's a difference of squares. So when you have a difference of squares, you can quickly go to the factors by basically saying that if it's of the type x squared minus a squared, the factors will be x plus a, x minus a. So the first one here, if we have x squared minus 36, that is a difference of two perfect squares, so it should have factors x and x, 6 and 6, square root of the first term, square root of the last term, but one would have a plus and one would have a minus. And then when you check by using your distributive property, x times x will give you x squared, minus 6x plus 6x will be your inside and outside products, which would cancel, and then you'd be left with your 6 times negative 6, which would be minus 36. So you can just quickly check it to make sure it's right. So this one here has that difference of squares type as well, so it has perfect square. For the first term would be 3x times 3x will give you the 9x squared, and the perfect square for 16y squared is a perfect square because 4y times 4y gives you 16y squared, and there's a difference between the two of them, so that is a difference of squares, and it has factors. The square root of the first term, which would be 3x, and the square root of the second term, which would be 4y, would be the second terms in each of your factors, but one would have a plus between them, one would have a minus. And it doesn't matter if you put the 3x minus 4y first and the 3x plus y second, 4y second, or vice versa, you'll still get the same answer. I like to put the plus first for some reason. Okay, so the next one is not a difference of squares. There is a difference, but 8x is not a perfect square. 32x cubed is not a perfect square. But first rule of factoring, always check for a GCF first, right? And if you look at this one, there is a GCF of 8 and x. And if you take that out of the first term, you're left with 1. And if you take it out of the second term, you're left with 4x squared. So what's left inside, though, is a difference of two perfect squares. So it would have factors. You still need the 8x because it's still a part of the original, and you would have 1 and 2x, 1 and 2x, plus minus. Okay? All right, so let's try a few examples. Oops. All right. So the first one is just getting you to practice expanding again. So we'd have x squared minus 2x plus 2x minus 4. And that would give you, those would cancel, and you'd be left with x squared minus 4. So if you recognize, again, the patterns, that's going to happen all the time. You're going to have inside and outside term products are going to cancel. So if you recognize right away that this is just a difference of squares factoring, you can go straight ahead and skip that kind of middle step now and say, well, this has a difference of squares pattern for factoring, so this should be just x squared minus 9. And the same thing with this one, has that pattern of x plus 6, x minus 6, so you know from your work with difference of squares that we just did that should just be the 6x and the negative 6x are going to cancel, and you're just going to be left with x squared minus 36. All right, so next question asks you to come up with some numbers that would kind of work backwards from the factors. So if you had factors x plus 5 and x minus 5 and x plus 5, you would end up with x squared minus 25. And x minus 11, x plus 11 would be x minus 11 squared, or 121. And this one would be y squared, because the second term is y in both of those factors. And the last one should be 2y squared, which is 2y times 2y, or 4y squared. So some practice here at factoring a difference of squares. The first one is a difference of squares, and the factors would be x and x plus 1n minus 1. This one would be x and x plus 4n minus 4, because the square root of 16 is 4. Square root of 49 is 7, so we know, and the square root of x squared, of course, is x, so that would be x and x, 7n. 7, but 1 would have to be a plus, and 1 would have to be a minus, so that when you multiply them out, the inside and outside cancel. Again, this is a difference of squares. First, square root of the first term would be x. Square root of the second term would be 8y. So you need 1 to be plus and 1 to be a minus. And the next one, we'd have x, and the square root of 25 over 4 is the square root of 25, which is 5, over the square root of 4, which is 2. So we need 1 to be a plus and 1 to be a minus. And this one would be x and x, and the square root of 1.44 would be 1.2, but you need a y with that. One would be plus 1.2y, and the other one would be minus 1.2y. The decimal's not real good on that one there, but the more I try, the more worse it looks. Okay, so this one here would be 3x and 3x, 8 and 8, plus and minus. Again, it has to be a difference of squares factoring in order to have these factors. Now this one has a star next to it, and you'll see why now in a minute, because the square root of x to the power 4 is x squared. So the first factor would have x squared, second factor would have x squared, and the square root of 16 is 4, so this would have 4, and this would have 4, one would have plus, and one would have minus. But you're not finished, because the first factor is not much you can do with the sum of squares, so that would stay the same. But this factor is a difference of squares again, so that can be factored further. So that would have factors x and x, 2 and 2, one would be plus and one would be minus. And the next one, we have difference of squares again. 149 are both perfect squares, so this would be 10 and 10, and 7x and 7x would give you 49x squared, but one would have to be a plus and one would have to be a minus. Okay, the next one looks like it can't be factored as a difference of squares, because 3 and 75 aren't perfect squares. But if you look at your first rule of factoring again, you will see that that binomial there has a GCF of 3. So if you take out, put a little star there to remind GCF. So if you take out your 3, you'll get x squared minus 25. And sure enough, what's inside is a difference of perfect squares. So that can be factored further as x and x. With 5 and a 5, one would be plus and one would be minus. And the next one is again a difference of two perfect squares. Square root of 81m squared would be 9m. And the square root of 121 would be 11. And one would have to have a plus and one would have to have a minus. And the next one is, again, it kind of looks like a difference of perfect squares, except 162 and 2 aren't perfect square numbers. So if you, again, check for your GCF first, you can take a 2 outside, and you'd be left with 81 b to the 4 minus w to the 4. And that binomial left inside would be now a difference of two perfect squares. So you can go one step further and write that as 9b squared and w squared. One would have to have a plus and one would have to have a minus. And you should notice, again, if you check your factors again, that the sum of squares you can't do anything with, but the second factor with the minus in it is again a difference of squares. So that can be factored again as 9b squared plus w squared. And then this would be 3v plus w, 3v minus w. And there's nothing more you can do with that now because none of the factors that are left have any, there's no GCF, there's no difference of squares, and they're not trinomials, so you're done. All right, the last two examples now are going back to the trinomials that have two variables in them. And basically, you kind of look at these, again, they will be, if you look at the second variable, like in this case, the second variable, the new variable that's introduced is a d, we kind of ignore that for a minute and treat it as if it was 5c squared minus 13c plus 6. You'd be looking for two numbers which multiply to give you 30 and add to give you negative 13. So you're going to do basically the same thing as you did before, except when there's a CD, a combination term, and then a d squared on the end, you got to remember in your second factor to put a d in your second factor. So we just, again, factored basically the same way we factored as if the d wasn't there. And the two numbers that multiply to give you positive 30 and add to give you negative 13 would be negative 3 and negative 10. Because the two negatives multiply to give you positive, and when you add them you get a negative 13. So then you can use your decomposition or your box method, whatever you want to use, or guess and check if you want to use that. I'm going to stick with decomposition. So we've got 5c squared, and then we've got minus 3cd minus 10cd plus 6d squared. So we're just basically doing the same thing, but except this time we've got a c and a d in the middle term and a d squared in our last term. So then we find the numbers. That's the first step for decomposition. Break it down, which was the second step we just did, then group and GCF. So we'll take a look at the first group. The only thing that's common to both of those is a c, and what's left inside would be a 5c minus a 3d. And if you move to the next factor, if it starts with a negative, take it out. And if you look at 10cd and 6d squared, well, 2 goes into both of those, and a d is a factor of both of those as a GCF of both of those terms. So then if we factor it out of the first term, we're going to be left with a positive 5c, and out of the second term, if we divide the negative out, we're going to have a negative, and it's going to be a 3d. And these two are the same again, so they would you pull them out as a GCF now. So you'd end up with 5c minus d, and then if that's pulled out of the first term, you're left with c, and if it's pulled out of the second term, you're left with 2d. So those would be your new factors. Now if you want to use the box method is basically, if I just review it with you, your box method, you'd still find the two numbers, but then instead of breaking it down with a math statement, you would put them in the box. But the first term, 5c squared, would go here. The last term, 6d squared, would go in the bottom. And then it doesn't matter which box you put the negative 3cd and the negative 10cd. So I'm going to put the negative 3cd here, and I'm going to put the negative 10cd down here. And then if you remember, with the box method, you look at each row and factor out the common factor of each row. So in the first row, there's a 5c squared and a negative 3cd. So the only thing that's common to that row is a c. And then you look at the second row, you got a negative 10cd and a 6d squared. If you remember from when we did the box method, if the row, the first element in the row has a negative, take it out. Even if it's not in both, if the first element is negative, take it out. And the same thing with your columns. If the first element, the top element in your column, is negative, take the negative out with your GCF. So the GCF between 10cd, or negative 10cd, and 6d squared, you'd need a 2, and a d would be common. And then if you look at the column, 5c squared minus 10cd, there's a 5 that's common there, and a c. And if you look at the last column, negative 3cd and 6d squared, you have to take the negative out. And there's a 3 and a d that's common. And they would be your factors. Now, you're not going to get full marks on a question if you leave it like that. You actually have to write it in factored form. So you would have to say 5c minus 3d. and c minus 2d. Now it doesn't matter the order of the factors. If you wanted to say the c minus 2d first and then the 5c minus 3d second, that would be fine as well. Okay, so the last one there is basically the same type of thing. So you'd be looking for, again, if you kind of ignore that q, you still have that form that the first one has a p squared, the last one has a q squared, and the middle one has a pq. So if there are two numbers that multiply to give you 3 times negative 2, which would be negative 6, and add to give you negative 5, then this is factorable. So what two numbers multiply to give you negative 6 and add to give you negative 5? That would be negative 6 and 1. So if we're using decomposition method, we found the numbers, then we break it down. Find the numbers, break it down, group and GCF. Find the numbers, break it down, group and GCF. So we found the numbers, now we're going to break it down. But we have PQ with each term. So plus 1 PQ. And then minus 2q squared. And then you group, and you take the 3 and the p is the GCF of the first group. And you're going to be left with p minus 2q, yes, 2q. And then the next group, there's nothing in common, so you just take out a 1. No, there's a q in common, sorry. So you take out the 1q or just q. And then there'll be a p minus 2q. So then you've got, if you look at this group here now and this group here, they both have a p minus 2q. So we take that binomial out as a GCF, and we're left with 3p plus q. So your factors would be p minus 2q and 3p plus q. So we check using the box method if you want to do it that way. Just, you don't have to do it both ways. I'm just showing you both ways. So this would be, you'd put the first term here, you'd put the last term here, and you'd put the combination terms with using the numbers that you found from here. The negative 6 and 1 would be negative 6 PQ and the 1 PQ. So both decomposition and box method have to start off with this first step of finding the numbers. And then with the box method, you look at each row in each column and take out the GCF of each row in each column. So for the first row, the 3p squared and the minus 6pq, there is a common factor of 3 and p. And in the second row, you would have q, is the only thing that's common to both of those. In the first column, 3p squared and 1pq, there is a p. And nothing else in common. And then the next row starts with a negative, so you got to take out the negative, and 2 goes into both of those numbers, and both of them also have a q. So that would be your common factor of that last column. So therefore your factors would be the p minus 2q and the 3p plus q, which is the same answer we got when we did it using decomposition. So there's some questions there at the end there that you can try now in the textbook to help you practice some of these skills that we've learned in this section.